Hello, everyone. I just want to talk to you a little bit about my project on divide and conquer. Uh, this is a fun project. I'm definitely going to love this class. I chose to do mine in C Sharp, so the .NET framework. I'm using .NET 5, which is based on what they previously called .NET Core, which is cross-platform, open source, all that good stuff. .NET 6 is currently in preview. I thought this would be kind of fun doing this in the .NET framework. There's a lot of overhead in the .NET framework. It does a lot of things. It's got garbage collector. It's got just-in-time compilation. So some compiling gets compiled originally to intermediate language, and then once you run it, it will then compile it onto the target system. Kind of like it's similar to how Java works. I just thought it'd be kind of fun to see how it works on here. Now, had a few goals that I wanted in mind. I kind of wanted to create my algorithms to be useful in the real world and so on. And when I say that, I mean I want them to be usable by an actual person that might need them for their project. And typically that means you want to make it use built-in collection types. Especially interfaces are very nice because then it doesn't matter what kind of collection you have as long as it's the right style. For instance, I created it so it uses a list, and a list is basically in C Sharp, it's a collection that's indexed. So it's kind of like an array. The advantage over an array is you can add items to it and take items away from it. So I'm going to go ahead and share my screen first. I kind of want to show my code off a little bit here. Now, my code might change slightly when I turn this in. I've been making some tweaks to it, things like that. But let me go ahead and share my screen. Now, when you're looking at my code here, I created extension methods. And in C Sharp, extension methods allow you to create static methods in a static class typically that extend the functionality of objects to where you can make methods that look like they are members of that object, even though they are not. It's used extensively now in the framework. For instance, the built-in sort function for a list is not actually part of the list object itself. It's actually an extension method. But when you include the namespace for that has that static class for extension methods in your own project or in your own class, it will carry that over, and automatically when you hit the dot after your object name, it will show up in IntelliSense. So it'll give you a list of all the members of that object. Well, it'll show up as if it's a member. It's kind of syntactical sugar. It's not something that you have to, that changes anything. You could do it the old-fashioned way. It just looks a little cleaner in your code. It's a little more readable. Okay, so let's get into this. In my list extensions, I just have a static read-only random object, and that's just for doing random numbers. No big deal there. But as far as the public side goes, I have a swap extension that just swaps two items. I just decided to make that public, and because that's always useful. Somebody could use that for swapping two items. Comes in use for a lot of things. I did a bubble sort. And the bubble sort is very straightforward. There's no recursion going on. It's just a couple of loops, for loops. It's very slow. I will point out one thing that I didn't use list type or list T. In C Sharp, you have generics. It allows you to choose what type of object or value type is stored within that list. So T is just where you see that right there with the T. In code, you would replace that with whatever type you want stored in the list. So it's all type safe, strongly typed. But anyways, I chose to use iList, and that's an interface. The advantage is it doesn't matter. You don't have to use a built-in list. You could create any kind of collection as long as it implements the interface iList. So it will have things like the indexer and so on. I did that because you could do an array actually implements iList. So you could create just a basic array and use that, and it would have bubble sort as an option. It would look like it has a member function of bubble sort. But anyways, so we got bubble sort here. Down here we've got quick sort. But all of these, when it has that this iList, the this is for extension methods. If you called this directly, you can. It's not typically done for extension methods. You can call it directly, and the this really doesn't have any effect on anything. Don't quote me on that. I'm not an expert on how the inner workings of the .NET framework works, but anyways, this is very important for extension methods, which allowed you to do all the fun things that I've been talking about on that. But anyways, we have a quick sort here. Also just takes a list because that's what it's operating on. So when if I was to type in, if I was to make a new list, and I was going to say, if I hit test, hit the dot, if you will notice, look at there, it's got bubble sort right there. So it looks like that's part of test. You'll find merge sort, quick sort, button, and sort. And if you notice, sort is a built-in one. But here's a little quirk. Well, it's not really a quirk, but it's just a limitation of the framework, which some people kind of complain about sometimes. If I make this an iList, which is perfectly acceptable to create a list, to create an iList that contains, I don't want to say contains a list, but to use an interface for my variable, and it's actually pointing to a actual list. If I do this with my extension methods, you will still see bubble sort and all those. But if you notice, sort is missing. That's because the extension method in the framework for sort only works on list itself, not iList. That was something they chose to do. Internally, lists use arrays that are use some creative things to allow them to grow and not have too much overhead on growth. It kind of predicts where it's going. But anyways, that's just a little tidbit there. But it as you can see there, it looks like it's part of that member variable. But anyways, a part of that object members. Anyways, got quick sort here, and all it does is call the recursive quick sort method, starting with the very beginning of the list and up to the very end, which is obviously count -1. Watch out for those off by one errors. It's always very tricky. But anyways, then there's a recursive function for quick sort. As long as low is greater than equal high, or sorry, excuse me, as long as low is less than high, it will go ahead and do the quick sort on the two sides of the partition. Anyways, and it calls itself twice for the low and for the high. Keeps doing this. Not a lot of exciting things going on there. Most of the exciting stuff happens down here in the actual partitioning. If you notice, I just keep passing that same list from one to the next. Pretty standard. I'm just using a list. If you see some of the examples on the internet, they might use arrays, that kind of thing. Well, I chose to use iList. So it could be an array, but it might not be. It might be an observable collection. I'm not going to go into what an observable collection is, but it inherits from list or iList. You could have a read-only collection. There's all kinds of things that inherit from iList. In this case, iList T. It's important to denote the difference between the base iList and then the generic iList. But anyways, there's one little wrinkle. I found out in my testing that if you don't randomize the pivot, it will cause some significant slowdowns on certain types of certain data sets for your input. I'll call it that. And for a while, I actually had it where you could choose if you wanted to have the random pivot or not. I eventually just got rid of all that. I still have some data for that and some graphs that I have in my report just because I thought it was interesting, but it really does not perform near as well. The way Quicksort works, if you have an idea of what kind of data you're having coming in, because when you think about it, data sets are rarely purely random. There are purely random inputs out there, but a lot of times it's somewhat in sequence, but kind of not perfect, or it's mostly in sequence, but just a little random, or mostly random, little in sequence, that kind of thing. So I chose to just leave it at random. Most things that I blog posts and things I read about it, most of them will say that random will generally give you the best performance, unless you have a specific type of data set in mind that you might be able to optimize for. By default, it just starts with the pivot is whatever the low what happens to be at the low value. But anyways, or the low index, I guess you could say. Pretty standard. There's two major partition schemes for Quicksort, and it does have an effect on performance. I'm not going to try to pronounce the guy's name. If you look up the background on Quicksort, you will quickly see the information on that. But the guy that invented it used the style that I'm using here, basically a big while loop, and inside of it, there's a couple of do while loops. The other way is simpler, a little bit simpler. It's maybe easier to explain. I'm not sure why anybody want to use it. Other than that, this is not really that complicated. So I went ahead and used this. It definitely gave me a bit of a performance increase. I would love to show the differences there, but it starts getting kind of crazy with all the different things that I'm showing in my testing framework, testing fixtures, as our instructor has told us. But anyways, yeah, getting off, losing my train of thought here. Sorry about that. But anyways, it's just a basic Quicksort. Of course, here we're using the swap extension that I mentioned. All right, moving on down. So I know this is going to get kind of long. I apologize. Merge sort. One thing with merge sort, a lot of the examples I see, it will create temporary arrays inside of the merge method or merge function. That means you're creating lots of arrays over and over. And if you know, I'm also going to point out the fact that I am using an array here. This is internal. Nobody's going to see this. Nobody, if you're implementing this sort function, nobody's going to see that. So there's nothing wrong with arrays, and they're absolutely used in C#. But a lot of times for public facing parameters and stuff, unless there's a good reason, you're usually not going to directly use arrays, except for buffers, things like that. Of course, you'll use arrays, but internally, there's no reason not to use an array. And I know from experience that operations on arrays, like iterations and things, they're faster on pure arrays than on, for instance, a list type, a list collection in C#. But anyways, what I did, I wanted to try to get the most performance I could out of merge sort. And so I created one temporary array, and it's just the same length as the list that we're passing into this this method. And that's of note. Merge sort does require, at a minimum, you're pretty much using double the memory, because you have to create an entire array or a whole bunch of small ones over time. It's eventually going to use that same amount of memory. But yeah, that's important to note. So we call the recursive function or method. We keep calling that over and over, of course, because it calls itself. And it's just a basic merge sort, divide and conquer. You keep dividing it up and then putting those two in order, and then starting off dividing it in the middle, divide that in the middle, you divide that piece in the middle, you divide that piece in the middle. It's it just keeps working down. It's almost like a fractal in a way. Pretty straightforward here. Not a whole lot to go over here, but we do call, of course, after we recursively call merge sort on each leg, I guess you could say, each side, then we merge them back together, and that's in the merge there. So now get down to the merge. This is where all the magic happens. We've nothing too crazy going on here. Just a basic merge sort. Just found one nice implementation off the internet, and I based mine on that. Did a few tweaks. Like I said, you can see my temporary array right here. I had done it with two separate arrays, a left and a right. It didn't really, it's not that big of a deal. It's just as easy to use one array. It's all internal. Nobody's going to see this. It might be a little harder to follow if somebody's looking at it. And basically the main difference is anytime you're using the right side, which will always end up being J, and I always keep it using J on here. Most implementations will have that. We'll use J for the right side iterations. You just always got to make sure you use middle +1 for the index. That way you don't get the two mixed up and you're overriding things and so on. And it's important when it merges that back into your actual list or your original array, your original data set. So this right here, these two, that's all that's doing is copying everything over into the temporary array. What we have right now, straightforward copying it over. Then down here you have the fun stuff. It's doing the while loop. It's actually going through and comparing. Now, I should note, I'm going to go up a little bit. Sorry here, I'm jumping back. If you notice, in most implementations, you'll see something like array I less than, you'll see something like that. There's a reason why I don't use that. I can't use that. And I'll explain why. And it's the same situation down here in merge sort. I cannot use that. And there's a good reason for that. I'm using a generic, this is generic. This method has no idea what type of object is going to be stored inside of that collection. Not every object can be compared to another object. How do you define if a string, if two strings are greater than or equal to each other? Do you base it on their length? Do you base it on the actual Unicode values of each character and add them up? How do you do that? There's tons of ways you could do it, and there's no way that my sort method could understand that. So for every method in my extensions, there is a where clause on or where it's basically a constraint. It's saying it's more of a constraint. I'm not sure exactly what we exactly call this. I have to go look it up. I'm not great at remembering terminology, but I know what it does. Where T, so this is for the generic T, it's going to make sure right here that it has to implement, so whatever object you pass to this method, it has to implement iComparable T. And iComparable T provides certain methods that have to be implemented by that object. Compare to, and compare to will compare, you know, the object on the left, compare to, it will compare it to the one on the right. And if the one on the left is less than, it will give you a negative number. If it's greater than, it will give you a positive number. If they're the same, it'll be equal. So you can use it for comparison's sake. Works great. So this could impact performance slightly as opposed to using pure arrays and non-generic methods, but I wanted to make this something that would be useful to anybody that implements it. Not trying to eke out absolute every microsecond, you know. But so this is where all the comparisons happen. If it's you know, it's basically doing iterations on the left and right side together through, you know, instead of doing separate iterations on each side, but it's doing all together. Then we get down here, and this is where we actually put everything from our temporary working arrays back into our original list. So anyways, that's a long-winded, probably too much information. Nobody cares about my code. They just want to, you know, see what happens with it. But let's bear with me just a little bit longer. I'm going to talk about my the actual program that the testing fixtures, I guess you could call it. So here's my program class. This will have the entry point to the program main, which is right here. If you notice, it's private. .NET Framework doesn't care. You can make this public, internal. It always will be able to call main. I usually try to approach things as making it as restrictive as necessary, or as restrictive as I can while still being usable. Just the general practice. So if I can make something private, I'll make it private. If it needs to be internal so it can be accessed by other things, it's not something I use too often, but you know, I'll use internal. Only make it public if it needs to be public. That way implementers don't have access to stuff they don't need to be directly accessing, because it can break things. But anyways, again, just have a random object for doing random numbers. I have a stopwatch. I just create it one time, read only, so I can't accidentally change it. It's just a stopwatch, nothing crazy. It's in the system.diagnostics. It's accurate down to very small amounts. I actually measure my performances in milliseconds. You can actually go all the way down to ticks, which I have to look it up. It depends on your platform, things like that, how much a tick is. I want to say a tick is 100 millisecond. It depends on your system. But anyways, the entry point, we're just doing two things. We're validating and we're running the test. And what is validate? Well, as I was tweaking some of my algorithms, you know, I break things. Don't always notice that I break something, and it's doing wacky stuff with the sorting. It's putting things in crazy order, whatever. I had a quick little validation in here that will simply use a random unsorted list, 20. I want to make this displayed on the screen so you can see that my code is actually working. And then I do a sorted list, and this sorted list gets sorted by the built-in sort function. And I'm going to assume that the Microsoft developers and so on that came up with this know what they're doing, and theirs works. So that's an assumption on my part. I'm sure it works. It's been seen by way more people than I could ever imagine. But anyways, then we simply I display the unsorted and the sorted list. That way you can kind of see what it should look like when it's finished. And then I simply validate. I call a validation on each method. Now I create a list for each one, and I copy. And when you create a list and you give it a parameter with another list, it simply copies that list into your new list. So this list will have a copy of unsorted list, but I don't want to actually mess up my unsorted list. I want to make sure they're all working from the same data set. So we create that, and then we call validate sort with that with the sorted list, so it knows what to compare it against. We pass the actual list, and this might look weird to some people if you haven't used C# much. This is a lambda expression. It's empty. There's no return type for this, but you can actually pass a parameter. So you can pass a parameter. You can pass an actual method to another method, and it's a delegate. Lambdas are a shortcut for creating delegates. I can create these manually. It's not very clean. You have to create a delegate variable and so on. But anyways, this just lets me pass the method bubble sort on my list. And then I'm just passing some little pretty stuff so it can print the name of what sort is being validated. I do this for every sort method except for the built-in, because we're already doing that right there. Move on down, validate sort. This is where it actually does the validation. Pretty straightforward. It takes in the list, the sorted list, takes in the unsorted list. Action sort action, that's where you can pass in a lambda delegate. Basically, you can pass in a delegate, and action is for one that has no return value. You would use func for one that does have a return value. You can also include parameters. If you did action, I don't know, I did this, it would be for a function that actually takes a list as a parameter. Now, when you actually you sort, this parameter is actually works like a method. So if you look down here, you'll see sort, and it looks like a method call. Now it's giving me IntelliSense is giving me a squiggly line. It's because it really needs to have a list in there. If I did that, it should be happy. Yeah, there we go. But we don't want to do that. It's already acting upon list because it knows when it gets passed in, that method is automatically working on that list. That parameter is basically automatically being passed into that method call in the method chain, in the chain. So we do the sort, we display it, we then go through, and that's just so I can visually see what it looks like. Then I loop through it and I compare every single item in my list and the sorted list compared to the good sorted list. And then if it fails, we give a nice big nasty fail at the end and we return, because I want to keep going. I don't want to stop the test just because of that failure. And then if it passes, we get a nice pretty pass at the end. We go back up. The next thing we do is run the tests. So running the tests. We're just calling test on get random list. We're passing in, this is basically another case where I'm passing in a lambda expression. I don't have to actually use the lambda pretty much here, because I'm not creating, like, I'm not doing anything crazy. I'm just passing in the method name. So we pass in get random list, get sequential list, get reverse list. And it's going to execute. That way I can, it looks complicated, it looks silly. Why am I doing all this? The only reason is I don't want to keep writing the same code over and over and over and over with just slight changes, and there's so much room for error. So if I can keep things modular and repeatable, it just makes it easier for me to maintain. So it's going to, the actual test method that this is calling for each one is right here. It takes a, as you can see, I'm using func here because this has a return type. Excuse me. Because it returns an integer, which actually contains how many milliseconds the operation took. And then it has, in the second item for the func generic declaration is actually what goes into it. It's a parameter. So it starts off with one. You have to have at least one generic type in here, which is your return type, and then anything after that, you can add multiple ones. I can add another one here if I wanted to. Those are all parameters that are required for that delegate function call. Anyways, we're going to call that get list. So this will make a little more sense when I get down here. We're just going to do a for loop. I've done this different ways. I did different tests. And originally I was just going by 500s. So it'd be 500, 1,000, 1,500, 2,000. That was fine for when I was including bubble sort. I'll talk about that in a second. But you couldn't go very high because bubble sort is painfully slow. It is incredibly slow. So I did some tests early on with bubble sort, and just to kind of compare it to the other ones. And then I was like, no, I want to go to the extremes. I want to go to a billion. Let's do a billion. So we're just going to start this test at 1. I was starting at 10, and I'm going to tell you why I'm starting at 1 now. There's a little quirk that happens. And it's a limitation. I'm not sure exactly what it is. But anyways, I start at 1 and we increment it. We're gonna do this by gosh, I'm losing my train of thought here. It's basically going to be by multiples of 10. So we'll end up we'll start at 1, then it'll be 10, 100, 1,000, 10,000, 100,000. And the reason I like that is because my graphs, when I'm doing graphs to show the time, when you have an O n log n, it's going to progressively get worse and worse in the time. So you're going to see a curve up on a linear chart, but the numbers get really big. So it's nice to use and you lose all your detail at the quicker times for the shorter, for the smaller data sets. So it's nice to use a logarithmic chart rather than a linear chart. Well, when you combine a logarithmic chart with using going by multiples of 10 on here, and the logarithmic chart is log 10, this is using 10, it makes it nice and pretty. So if a method is operating at n log n, it should be a nice, pretty 45-degree angle horizontal line if your graph is scaled properly. But it will be a nice increasing line. If it deviates from that, it's going faster then, which is crazy. That'd be extremely fast sorting. But it should, if it starts curving down and flattening out, it's worse than n log n. Anyways, just as you can see, I have bubble sort commented out. When I actually run this to show you all, a billion takes a little while. So what do we got here? Did I put a billion? I can't remember if I already shortened this down or not. 1, 2, 100. Okay, let's just drop this off a couple. And it's hard to read. It's hard for me to read a whole bunch of zeros in a row. Sorry, Paul. Apologize for me wasting time there. Anyways, moving right along. So this, what happens here? We are doing another. So this sort test right here will return. This actually returns a double containing the milliseconds for a single sort operation. We're passing in another delegate to a method. And what we're doing is we're just, I did this with a lambda expression because I'm just creating a new list. I'm doing this all in line because it saves space. I think it looks nice. We're just creating a new list and we're doing quick sort on it. We're doing a new list and we're doing merge sort on it. A new list and sort. So we're passing this method call in to sort test. We do a restart on the stopwatch. Restart just does a reset and a start all in one operation. And then we actually sort, and this will call each one of these as we go through here. And then we stop the stopwatch and then we turn the total milliseconds as a double. Pretty good precision there. And then since that's contained in a console.write, it's going to write that out. I put commas in here and then a new line at the end. /r/n is a shortcut for doing carriage return line feed. If you ever work with Linux versus Macs versus Windows, they all use a different style of Line endings. Windows uses a carriage return line feed. It's from the old days on printers when it actually moved to print head. Carries over even now in modern computer languages. And but anyways, if it uses just /n, it's just a line feed, which is, I believe, what Linux uses, and just a carriage return, I believe, is what Macs use. Anyways, there's a lot of programs that don't really care. There's a lot of the development programs for Windows don't really care. But anyways, it's outside the scope of this discussion. So let's go ahead, and so all it's doing is putting commas in there, and it's to make it pretty. It's not just for that. It's also so I can quickly select those items. As you can see down here in my debug console, you can see where I've already done some. I can just select those items, copy them, paste them into Excel, and it will create a nice little table for me. It makes it easier to work with. And that's the testing. Only thing left in here is these little helper functions that are just down here, helper methods that are just, this creates a random list. This creates a sequential list, and this creates a reverse sequential list. And I should talk about that a little bit. At first, I was just doing random, and I thought, not all data sets are purely random. Sometimes you get a data set that's already sorted, and some sorting algorithms, if it's already sorted, they will operate faster. Some don't care. Bubble sort does not really care. It's going to be slow regardless. It's going to go through the whole thing. It's a little bit faster, I think, actually, when it's sorted. Not to look at that, but I was trying to think. Oh, when I was doing the quick sort with a non-randomized pivot, if you do quick sort on a sequential list, absolute horrible performance. And it actually makes sense when you think about it, because when it's already sequential, if you're just starting with the leftmost or rightmost value as your pivot, it's already going to be completely unoptimized. The ideal is to pick, the middle value basically. And if you're starting at the ends on a sequential list, it's going to be horrible. That's where the randomized pivots come in. It makes it go faster. Also, when I did that, when I wasn't using randomized pivot, it was much more likely to run into Stack Overflow. I have no problems with Stack Overflow on any of these, even when I went to up to 1 billion elements. But at with quicksort with a non-randomized pivot, it would hit Stack Overflow. Dun, 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 dun. But there's ways around that. You can create a separate thread, and you can increase the stack space, basically stack size on that particular thread. That's kind of a kludgy way to work around it, but I didn't want to mess with all that. So let's actually run this. I'm going to quit sharing real quick because I like doing this in that regular console rather than the little debug console in here. So let me stop my share, and I'm going to share my Windows terminal. If you don't use the new terminal they have for Windows, I highly suggest it. It's great. If you wonder what's going on here with my command line, I cannot remember the names of these off the top of my head. It's hard to find when I don't know what I'm searching for, but you can do things to pretty up your console. This works great if you use Git, and I use Git for development. I love it. It's obviously used in the real world. Most corporations are going to use some kind of source/version control. I use Git. There's other ones out there, but Git is really popular, and I use GitHub for that, which some people hate that it's owned by Microsoft now. Whatever. Microsoft has their own Team Foundation services, or what I don't know what they call it now, but it's kind of tied in with Azure cloud computing. But anyways, they have their own, but you can use Git within that. actually. You can do some nice stuff like DevOps, and you can have builds, automatic build testing, and publication to a in Azure and do on your dev/release builds for web servers and so on. Way outside the scope of this class. But anyways, let's go ahead and run this program and let's see what it does. So we will do net run, and I'm going to run the release build. If you do the debug, it's a little bit slower, not a lot, a little bit slower. Release will do some optimizations that you won't get in debug. It can do some optimizations even with recursion. C# is not great about that. F# is a functional programming language, uses .NET. It's a little better about it. There's still some limitations there, but anyways, let's go ahead and run it and see what happens. There you can see my tests, and they all passed. Yay. That used a bit of a too large of a size. Let me go down. Let me break out of this. I don't want to make you all wait forever. So bear with me while I change to a slightly smaller max size. Losing my place in my own code. Okay, save that. Let's go back to here. Actually, you don't even have to build it first. If you run it and it'll end up building it in the background. So there you go. Wow, really fast. There's one little quirk, one little wrinkle here, and I haven't found a good way to work around it. The very first, it only happens on the very first one. The very first one will have a slow time for everything, and I think it's due to how the .NET framework works. There's probably, it's loading symbols, loading stuff in the background at the beginning. I've tried doing a little warm-up method that kind of calls all these same things, and it still ends up happening. I don't know. It's always the very first call will be slow. So that's why I actually moved it down to 1, which is nonsensical to sort. How do you sort one thing? Well, it's already sorted no matter what. But then I can kind of throw that value out. And I didn't for my report. I hadn't noticed why it was doing that. But anyways, as you can see, actually on my report, it's probably good because I'm noticing it right now that there's a weird little hiccup where on the speed of the built-in sort, where it gets slower and then suddenly it's faster than everything else. But as you can see, it runs through each one, comma separated list, comma separated values. The first one is random. Then you can see the times for sequential. Most everything performs a little bit faster on sequential. Just something I observed. And it doesn't even matter if it's sequential reversed. I want to say sequential reverse was also very slightly better performance than random across the board. Yeah, you can easily see that. As you can see, let's look at this one here. The first one is merge sort, or excuse me, quick sort. The second one is merge sort. And the third one is the built-in sort. The built-in sort absolutely crushes my results. But if you notice here, merge sort is faster than quick sort, but you can't always base that on each, some data sets, how it's randomized, whatever can affect things. You really have to run it a whole bunch of times to get good data. But that's, there's little quirks where one will be faster than the other. But I'm going to open up an Excel spreadsheet if I can find the one that I had used. This has got some junk in it. This one's actually not bad. I'm going to stop sharing my screen real quick and switch to that Excel spreadsheet. and show some results here. Okay, here is my Excel spreadsheet. As you can see, this right here, I got this old and new, but anyways, what we're looking at here is what my original data. I was doing bubble sort, quick random is what I called the quick sort with a random pivot, merge, and then framework. That's just what I'm calling the built-in sort. Please note these charts are logarithmic, so that's why we're going from 0.001, 0.01, 0.1. This is in milliseconds, up to 1,000 milliseconds. 1,000 milliseconds, that's 1 second. So as you can see, for these small values, they're very fast. That's why I had to measure them in milliseconds. Otherwise, I get lost. You can see here that some details that are going on here. I think we can't fully trust that first value. I really don't think I can trust that, because I think the very first run, it will always, that first one will have some poor performance. So I'm not sure I can really trust that. But as you can see here, the blue, that's a bubble sort. As you can see, it really, man, it's really slow. And it keeps getting just slower and slower, faster. The other one gets slower. I know logarithmic scale on charts is hard to read. It's not intuitive, but it's really the only way to keep the details in here. If this was not logarithmic scale, you'd see the, actually, I can actually change that real quick. There, you can see it. Bubble sort kind of throws out everything, throws everything else off. It jumps up there. Let's change the data we're using. Let's throw out bubble sort. There, you can see them all getting slower and slower, but it's not enough to really see that that curve that you would see. This is linear. The x-axis is linear. Vertical axis is linear here, but yeah, you can see here that the framework sort is absolutely crushing everything else. But there's a little wrinkle with the framework sort. It's actually a hybrid sort. It can use any of 3 sorts based on the data set that's involved. If it uses, if the partition size is less than 6, I have to look at my report here to remember this. It's less than 16, I believe. Yeah, if the partition size is less than or equal to 16 elements, it uses an insertion sort. If the number of partitions exceeds 2 log n, where n is the range of the input array, it uses a heap sort. And otherwise, it uses quick sort. But anyways, let's see what sequential looks like. If you look over here at sequential, you will see, let's change this back to logarithmic, and let me put back in my bubble sort. Okay, there we go. If you look over here at the sequential, you can see a craziness going on. Sorry, I'm jumping around here. Let's look at random again. Let's look at this one first, then I'll jump to sequential. You can see that the framework sort crushes all mine. Bubble sort, or excuse me, quick sort and quick sort and merge sort, they're neck and neck. You can't hardly tell the difference between these two. They are really, really close. I mean, if you get more details in there, try to zoom in a little bit, I guess you could say you might be able to see some slight differences. On this one, you can kind of see they kind of jump around a little bit. It's not really some of the results I expected. I'm kind of disappointed that I'm not getting the results I expected. Not 100% sure why. Maybe there's some details with my implementation that's not optimized. But merge sort, I would think, as you get to very large data sets, it should perform better, but it doesn't on here. And in fact, we'll see later on that it performs slightly worse than quick sort. Now, I've seen some information out there says that it might perform worse. It could actually be performing more operations that are for your particular language compiler, might actually slow it down a little more compared to quicksort. I'm not sure exactly what's going on there, but I know it has the potential to be faster in a best case scenario than merge sort. Just like, I guess in best case scenario, it has fewer operations or something. I don't know. But let's look at sequential. Sequential, this is where we see some weirdness. Quicksort without a random pivot performs abysmally. You can see that here. Same problem with a reversed set. Oddly, it performs a little better on reversed than it. Actually, I take that back. It performs the same whether it's reversed or sequential. It performs bad, but bubble sort performs even worse when it is reversed. Again, quicksort and merge sort are neck and neck the entire way. On this one here, we actually see quicksort performing slightly worse than merge sort in the beginning, and then they kind of even out. So I don't know. The framework always faster. Anytime you see a weird little hiccup like that, although I can see this happening multiple times, a little hiccup like that is probably due to maybe something happens in the background. The CPU gets hammered by something, and it throws off your result. That's why you have to really do these a whole bunch of times to get good data. But this is my first idea for testing, and then I went to this. What's going on here? Well, now we're going by tens here. So you essentially have a logarithmic scale, and this is also essentially logarithmic scale. So you have two logarithmic scales, and so everything is a nice horizontal line, nice and pretty, and this goes up huge. 10, 100, 1,000, 10,000, 100,000, a million, 10 million, 100 million, 1 billion. 32-bit integers, you can't go past, I don't have it memorized. It's a little over 2 billion on a signed integer for 32-bit. If it's unsigned, it's probably around 4 billion or so. If you use a 64-bit long, of course, that gives you way more to work with, but I feel like working with longs. Some methods don't take it, whatever. But areas can be long. You can have, and lists can use a long set of data, but it starts to get kind of crazy. But as you can see here, there's something that happens pretty consistently, and this happens even after that little hiccup that happens at the beginning. I think the reason why the framework sort of so far off in that very first one is because of that. But there's a neat little pattern that I saw on the framework sort. If you notice, it always drops, or actually always increases in performance when it goes from 10 to 100. That happens consistently, always does it. Then when it goes from 100 to 1,000, it decreases in performance slightly, decreases at a slower rate, decreases in performance. Then once it hits 1,000, the decrease in performance stabilizes into an n log n situation. And I'm going to show you how you can, this is n log n, but even though it's a nice straight line here, you can see that I still call this quick random. It's just, now in my code, it's called quick sort. It's, I'm just going to assume that it's best to just use a randomized pivot. You can see that these are very close together. They're neck and neck. I mean, it starts off with quicksort being slightly slower, and then it ends up with quicksort being slightly faster. It doesn't really make sense to me. It's not what they should show. I think it has to do with how everything gets optimized. It's fun. It's fun to see things like, I think, that don't work out like you want. I think that's still interesting. But it could show me that it's something wrong with my code, which that's irritating. Don't want my code to be wrong. My code could be bad, but I want it to still do what it's supposed to do and show what we're trying to show here. But still, it's interesting to see how much faster the built-in sort is. I know this video is getting long. I apologize, but let's see here. Looking over here, you kind of see similar things. There is slightly better performance for if it's already sequential. I know it's hard to look at charts side by side and compare them. You throw them all together and it starts getting being so many items, it's hard to see. It's really not a great way to do this, but if you just, I have them all lined up. So you can go across here and see that at this point, they're all performing faster on sequential. This one's performing faster on sequential. And it is a logarithmic scale, I keep mentioning that, but any slight difference in the upper portions of the vertical axis, slight differences are actually larger than they appear. Down here on the low end, differences are actually smaller than they appear due to the logarithmic scale. But let's do a quick change here. Let's change this to a non-logarithmic scale. What do we see here? Bam, it's doing that nice logarithmic curve. And if you can't see the details down here though. You lose out on all those details at the small one because it starts curving up fast. If I had smaller, if I wasn't doing a logarithmic scale down here and I wasn't jumping to such big numbers, you would be able to see more granularity in here and see a nicer curve. It wouldn't be so drastic, but it is what it is. That's what I have to work with here. Let's see. I could change. Oh, wow, I don't like working in. Let's just call it. Let's do that. We're looking. You can see at any scale, you're kind of seeing that same curvature. Still doing it. Still doing it. It's just hard. It's just not going to be nice and smooth. And it's going to be kind of crazy because it's jumping so much. These aren't linear values, so it's, you know, if it was linear values down here and you had linear here and it was nice smooth, you can see nice smooth curves. But anyways, it is definitely operating in log n. I could be wrong. I'm going to say it right now. I am not the greatest at math. Terrible for a computer science major. I'm not great at math. I don't know why. I just didn't study it that much when I was in school. I wasn't great at it. I didn't like it. I like aspects of it. I like it when it applies to programming. I'm probably not more the scientific minded for computer science. That's hardcore, pure computer science. You know, I hear that computer science, you don't even need a computer if you're doing pure computer science. You can, it's all, you can work it out on paper and math. But anyways, that's getting off subject here. I apologize. But I got my scales all jacked up now. Anyways, so my findings are that I really messed that up. My findings are kind of odd. I don't know exactly why I'm seeing quicksort perform better than merge sort. My Google foo, I've Googled it. You'll see things. This is why quicksort is faster than merge sort. But if you search for why merge sort, this is why merge sort is faster than quicksort. Sometimes I talk about you know, the size of the data set being a factor. Sometimes I've seen some mentions of the number of operations or best case scenarios for quicksort being being a little faster than merge sort. It could be the extra storage. not optimal. Maybe when I'm operating on lists, it's not optimal for merge sort, some quirk of that. There's so many uncontrolled variables. They're controllable, but there's just so many. I don't. It's hard to figure out exactly what's going on. But I know this video is long. I apologize. I am very long-winded. It's hard for me to break things down into short, concise. So I apologize for that. If my videos are too long, let me know. I will do my best to just hit the main things, not go into so much detail in the future. I hope you got something out of this. If anybody has any questions, let me know. Obviously, I love to talk about this stuff. I love to talk in general. Don't get me started. I am a motor mouth. But I enjoy this. I enjoy the discussions of this. Yeah, if you see something wrong with my code, let me know. I'm going to put it up on GitHub and make it public when I submit all this to the discussion. So anybody can look at it, see it. I think it's fun to work on code in a group on GitHub, which I don't do. I really haven't done that a lot. I've looked at other people's code. I've worked with other code from GitHub, but I haven't really worked on a team, which I think would be fun on GitHub. So if anyone wants to group up with me, if you don't mind having the old guy in your group that talks a lot and works a lot, hit me up. But otherwise, I hope you all have a great day. I hope you got something out of this, and good luck in your own projects.